Okay, so we're going to finish differentiability and continuity. We're just going to look at two more examples here. Let me see if I can find... Yeah, okay. So last time when we were talking about differentiability and continuity, to refresh our memory, so again, that's our notes, but here's was the old notes, right? So we sketched the graph of these functions that we were looking at, and then we wanted to determine the intervals in which it was continuous and the intervals in which it was differentiable. So we did 1 over x first, one we were very familiar with from our family of functions, right? The 1 over x there. All right, it's got the asymptote at x equals 0, so therefore we know it's not continuous at x equals 0, right? Makes the function undefined as well. So graphically and, in the function we can kind of analyze that there's a discontinuity there. Then we took the derivative using our old lame method of the limit rule, right? So now, and we got the derivative was negative 1 over x squared. Now we know that the shortcut there would give us the same thing, right? And so in the derivative, we would also see that what x value would give us problems. 0, right? It will make the derivative undefined. So where the derivative is undefined, therefore the original function is not differentiable, not able to be differentiated, okay? So we can't find f prime is 0, therefore the function is not differentiable at 0, okay? So that leaves out 0 in our interval there. Then we went down to a problem like absolute value, or function like absolute value, okay, slightly different. Here, okay, is the absolute value function of x minus 2, absolute value of x minus 2, is that ever discontinuous? Yeah, no, there's no jumps, there's no holes, there's no gaps, okay, anything like that. There's no asymptotes. It is what it is. It's a little v there, okay, so it's continuous everywhere. But when we go and take the derivative, which amounts to this weird piecewise function, right, because the slope to the left was always negative 1, the slope to the right was always positive 1, and so we had to come up with like a little piecewise function to kind of describe the derivative. At 2, where that pointy part is, okay, the slope suddenly changes from negative 1 to 1, so it's like kind of jumping in the graph of the derivative there, and so therefore the function f is not differentiable at 2, because we don't know what slope to say. From the left, it looks like the slope should be negative 1. From the right, it looks like the slope should be positive 1. If the left and the right don't agree, we don't have an actual value. 2 is, it's not, the function, or derivative is not continuous at 2, so we're done. All right, we're going to look at 2 more there in similar fashion. Okay, so the first one we're going to look at, excuse me, is the function following the same kind of directions here. F of x equals x to the 1/3. Okay, and we're going to sketch a quick graph of it over here. All right, so let's get our graphing calculators out and see what that thing looks like.
What, you can't do it in your head?
I know this graph.
Okay.
See what mode I'm in. Does that affect the graph that you're in like different modes?
So in general, so the question from Christian was about check to see what he wanted to check to see what mode he's in. Okay, and so in general in calculus we always want to make sure we're set to radian mode. Now with the thing we're graphing here, does it matter whether we're in radian or degree mode?
No.
No. In general, when you're doing graphs, the only thing that radian and degrees will affect is if you're graphing what kind of things? Sine, cosine, that kind of stuff. Since we're not here, it's okay to still be in degrees. However, I would say just as a general, kind of rule, make sure you're always in radians when you're in calculus. So even if it's something like this, just always check because you don't want to make a mistake and then mess up.
So you might be about to go over this, or you might not want to tell us, but is there a derivative function on your graphing calculator?
Yes.
Because it asks to use that on the homework.
Yes, and I will show you that in a second here, okay?
I was just wondering if that's something you do.
Yes. So let's graph this bad boy. And there it is. Okay, nothing too crazy. It's basically like a cubic function that's been rotated, right? Okay. All right, so it looks pretty good. So let's see here. Well, let's discuss the continuity of this. So we can discuss it by looking at the function or at its graph. God bless you. Okay.
You gotta go.
It's okay. I'm sure you'll be fine. You might just have to wait in line a little bit longer, that's all.
No, I'm gonna go on a field trip.
Oh, you're going on a field trip. Have fun. They left without you. Just kidding. They would have called or something, I'm sure. All right. So, what would we say our continuity is here?
All real.
All real numbers. So I'm going to say negative infinity to infinity using interval notation. But yep, all real numbers would be a good way to say it. All right, and then to kind of discuss the differentiability, well, one thing we kind of look at here is just looking at the graph, okay? Sometimes we can visually inspect, right? For example, if we had an absolute value function, okay, what did we see, what kind of like, how did that differentiability problem at 2, how did that show up in our graph here? We had like a point, right, a pointy part of our graph. Do we have a pointy part of our graph here? Yeah, not really. It looks pretty smooth, like it's a smooth curve. So we don't have any points, but we still could have maybe some other, kind of non-differentiable thing. So to do the derivative here, all right, let's actually just use our function. Let's use our power rule that we know. So I'm going to do it kind of over here to the side. So f prime of x, well, let's see here. So let me go, I'm going to pick someone. So Joey, what would be the derivative here? Of of x to the 1/3.
I gotta write it down.
That's okay.
Okay. So it'd be 1/3.
1/3 x to the
Negative 2/3.
negative 2/3. Good. That's it. That's our derivative. Which we should probably rewrite though, right, Joey, as 1 over what?
1/3, then on the bottom it'd be 3 root x to the
Yeah, cube root of x squared.
I know you said
If you just leave it as x to the 2/3,
like a multiple choice, it would be that.
right, chances are you want to be comfortable with like moving in and out of having the roots there or having just the fractional exponent, but I can almost guarantee that on a multiple choice you won't have a negative exponent. So you really want to make sure you're comfortable with like getting those to be positive accurately, right? Yes. Yep. If you have, this is fine as well. Okay, because they're both going to indicate to us what about our derivative here. Are we going to have a problem value? Yeah, when x is what? When x is 0, because that's going to make us undefined here. Yeah, so that's a problem. So it looks here like we don't have a problem at 0, right? The graph, like the way I sketched it, looks fine. But at 0, clearly in the actual derivative here, the differentiability, I'm just going to write differentiable. Okay, it looks like negative infinity to 0, union 0 to infinity is how we have to describe that. Okay? Now, remember, a sketch is just a sketch. Let's maybe actually zoom in a little bit around that x equals 0 area. So, now, for those of you that aren't familiar with zooming, okay, you can manually adjust your window by going to your window button and then like just, making your window smaller by changing your x min, x max, y min, y max, or you can use the zoom command. Now there's zoom in, okay, which if you hit that and then just hit enter, it will zoom in on that area. Or alternatively, if you press zoom box, which is, I kind of like it. Okay, what zoom box does, if you use your arrow keys, oh sorry, I should move around here. If you use your arrow keys to like move around, you'll see you have this little cursor. Okay, and I like to put my cursor kind of like the upper left of the behavior I'm trying to examine. Hit enter, and it drops a point, and then you can move your arrows to open up that little box around the area you're trying to zoom in on, and hit enter again, and it will zoom into that exact area. So again, it's zoom, and then zoom box, the first one. And so I zoomed in there. I'm going to zoom in just a little bit more. On that section. As we get closer, as we kind of like zoom in at what's happening right at 0, what kind of slope do you observe?
Undefined.
Probably a vertical slope right in there. And in fact, at the instant of x equals 0, we're going to have a vertical slope. Okay? We're going to have a vertical slope. Yes. Get your pictures.
Goodness.
Okay, now. Okay. Now, we can actually use our calculators to find the value of the derivative at a specific point. So let me show you that. Okay, so I'll have to remind these guys when they come back. So I'm going to zoom back out here, so press zoom and then 6. That takes you back to the standard viewing window. So it takes you back to normal. Okay, now let me show you how to find the value of the derivative at a specific point. If you press second and then trace, guess which command we're going to use? dy dx. Okay, you'll notice nothing happens because it's waiting for you to type in a value. We want to find the value of the derivative at what point? 0. So I'm going to type 0, and you now see it says x equals 0, hit enter. Ooh. It says dy dx equals 100. We think it should be what? Undefined, okay, which in our case, undefined means like going up to infinity. So this is 100. Now let's see what happens if we zoom in some and then try it. So I'm going to zoom in and see if it works better this time. So now if I do, so I zoomed in once. Now if I do second trace, go down to dy dx and type in 0. Still get 100. Interesting. All right, let me zoom in here. It's a little concerning. Second 0. Still 100. All right, so here we have a calculator error, okay, because it should be undefined here, okay? It should be undefined. So that's why we have to be careful, always trusting our calculators, I guess. All right, but it should be undefined there, okay? I'm not sure exactly what's going on with the way the calculator is working here. But it works for other things too. So for example, if I go, back out and I do, dy dx, and let's say I want to find the value of the slope here at 1. Well, we know at 1, what should we get? Let's see, if I plug 1 in for my derivative, 1 squared is 1, cube root of 1 is 1, so it should be just 1/3. So if I type in 1 here for my derivative, you see it rounds up the last one, which again is a bit of an error, but it's still, 1/3. We can kind of see it there. Okay. The calculator is not doing the same thing we are doing to find the slope here. The calculator is using a numeric kind of approximation method that's very accurate for our purposes, but we are doing the very precise, mathematics. It's not actually taking the derivative and then plugging it in. It's using a numeric method. Okay? Now, believe it or not, you can actually also use this to, I believe you can also use this to graph the derivative as well, but you have to be like a little tricky, I think. And I'm not sure. Let me see here. So, another way you can find the derivative besides using your graph is if you press the math button, and I think, let's see, where is it? Yes, okay. So if you press the math button and you go down to number 8, which says n deriv, okay, which is for the derivative. Okay, now my calculator has this pretty type in it, so I can type in all the little things that I want to, right? But for those of you that don't have my nice calculator like this, yours is going to look something like this. Right? Mm-hmm. Okay. So for n derive, what that means is, I'm going to write this on your notes here too so you can have this. The first thing you type in is your function. Then comma. Then I believe it's like the variable... gosh, how do I say this correct English? It's the variable with which you're taking the derivative with respect to. Nope.
I'm definitely gonna want this part again.
You're taking the derivative. So in this case, we want it generally we want to take the derivative with respect to x. So it's the variable.
Using the variable you use in the derivative.
The variable you're taking with respect to, no.
Basically, you're screwed if you don't have one of these. The variable you use in the derivative.
It's basically the variable you're taking the derivative with respect to. Variable
Oh man, you're gonna have to.
You're taking the derivative with respect to. So like, okay, I'll just say this: derivative with respect to blank, and that blank goes right there. So if it's the derivative with respect to x, you take the you put the x in there. If it's derivative with respect to y, you put a y in there. If it's derivative with respect to t, you put a t in there.
But can't you like only put in x for your variable in your calculator?
You can use alphas, I think, and stuff like that. But
okay.
yeah, in general, you're going to use x. And then I think there's a further command here. Let me just check to make sure. Hang on. So like 3x plus 4. Oh wait, comma 2. Actually, is what? All right, comma 2. Okay, and then the final blank is the f prime of the blank there. So you want to find whatever value you're trying to find. Okay, right. It's more complicated to do it, but sometimes we want to use this just to help us. So as an example, here, let's say I wanted to use my calculator to find the value of the derivative of x to the 1/3 with respect to x. So for example, if I want to write like, find f prime of 4 if f of x equals x squared plus 2. Okay, let's say we want to do that. So then I would use n deriv, parentheses. My function is x squared plus 2. I'm differentiating with respect to x. And I want to find the value of the derivative at 4. Okay? Your calculator will not just give you the general derivative. So for example here, we know that f prime is what in this case?
It's just going to be 2x.
It's 2x. Your calculator will not be able to come up with that 2x. But if you ask the calculator for the value of the derivative at a specific point, it can come up with that. So that's why we have to type in the 4 there. So I type that in. X squared plus 2, x, and then 4. We know our answer should be what?
8.
Yes. And so if we type that in, we get 8. Okay? We get 8. Okay? So questions on any of that? I want to introduce that now, though, so that way you can see that. Okay. Yikes, that was loud. So anyway, differentiable, so going back to what we talked about here, though, so this actually does have a vertical asymptote right at the instant of 0, because we can see that showing up in our derivative. All right, we're going to look at one more here, and then we'll be done. I'll give you guys time to work on your homework and stuff. Okay. F of x equal to 3x minus 2, negative x plus 6. It's a piecewise function. X less than 2, x greater than or equal to 2. We're going to sketch this as well. Okay. All right, so let's see here. So 1, 2, 3, 4, 5, 6. Okay, so 3x minus 2, so minus 2, and so we'll just, for x, less than 2. So I'm going to go ahead and graph this piecewise function, something we should be comfortable with, right? So this piecewise function starts, or I guess it switches at 2. So I'm going to graph that kind of like end point of this thing. This top part is only true, right, for x values less than 2. So, start at 2 here. 2 times 3 is 6, minus 2 is 4. So the x value of 2, we're going to go up 1, 2, 3, 4. And what type of dot should I put there? An open circle, right? Because it's for x values less than 2. We're not including the 2. So this starts at an open circle right there. Okay, at 2 is where it kind of like ends, I guess I should say. And then to graph more points from this, what x value should I kind of plug in?
1.
Get numbers that are less than 2, right? So we'll start at 1. So like 1 times 3 is 3, minus 2 is 1. So 1, 1 is a point. 0 gives us negative 2. And I'll do one more here just for fun. Negative 1 times 3 is negative 3, minus 2 is negative 5. So 1, 2, 3, 4, 5. And so we connect the dots. Okay, so there's our one side of our piecewise function. And then we'll do the other side. Okay, now it's for x greater than or equal to 2, so we'll plug 2 in. 2 times negative 2, I guess, plus 6 is 4. So 2, 4. Oh, well that's nice. It fills in our dot here. So 2, 4 fills in the dot. And then we'll try another point, so like 3. Negative 3 plus 6 is 3, so 3, 3. And we know it's just going to go down one, right one from there because of the slope. Something kind of like that. Okay, there's our piecewise function. Questions on that so far? Okay, now, for those of you from Miss Steinfeld's class, Brittany, you know how to do this. You were here when we showed this, right? How to graph these on your calculator? Were you here, Maya, when we did it? No? And then Connor, I guess you weren't here either when we did this. Okay, and then Jack, you don't know either then. Okay, so let me show you guys real quick, crash course, how to do this on your graphing calculator. Okay, you can graph piecewise functions on your graphing calculator. Okay, also helpful. We need to be able to sketch them, but graphing them is also, you know, a good thing to be able to do too. So, the piecewise function is made up of 2 pieces. That means each one of those pieces will take up a y equal. So the first one, y1, will do, in parentheses, 3x minus 2. Okay, it's important that you have your whole, like, piece in parentheses. Because what we're going to do now is divide that by, and we're going to divide it by the argument x less than 2. So I'm going to put an x. Okay, now the less than, for those of you guys that were here before, how do we find the less than symbol?
Second math.
Second math, and takes you to all the inequality symbols there. We want to go to the less than. That's number 5. 2, close parenthesis. Enter.
So would you have a fly in your left shoulder?
Neat.
Almost.
Didn't get it?
Yeah, what's the Ben and call one?
I've done that once. Unfortunately, no one was in my classroom when it happened, but I was just like, ha! And I was like, me. Oh, I felt like a ninja. No, I didn't want to kill it because I wanted to make sure I had it in my hand first. I don't know. I guess I could have just done that and then looked the guts afterwards too. But all right. So same deal for the second piece. Oops, second test. Greater than or equal to, boom, and then 2. Okay. Once you do that, you hit graph. Lo and behold, there it is. Okay, piecewise function. Okay? The way this works, in case you're curious, okay, again, you guys had already seen this before, you already know, but the way this works is that this top one, the y1, okay, it graphs 3x minus 2, but then for this x less than 2, it returns, like the calculator returns a 1 for all the x values that are less than 2. As soon as x becomes, you know, equal to 2 or greater than 2, it starts returning a 0 and thus makes that undefined, and so the calculator won't graph that part of this function. Same deal here. It's going to graph, the calculator graphs this as long as x is greater than or equal to 2. If x is less than 2, it's going to return a 0, making this undefined, so it won't graph that piece. And that's how it makes that piecewise function work. Okay? So, knowing what we know then about piecewise functions and continuity, is this piecewise function ever discontinuous?
No.
No. So, negative infinity to infinity. Using what we've kind of seen about differentiability, okay, it's not kind of, using what we've seen about differentiability, do we see any behaviors in the graph of f that might cause us to think it will or will not be differentiable somewhere?
Yeah, at 2.
Yeah, so at 2, okay, at 2, why might we say that it's going to be not differentiable there? Because we have a pointy part of our graph, okay, I know that's not very calculus, you know, it's not very, like, official, bless you. But yes, this point indicates that our graph is not going to be differentiable there. Okay? So, we can kind of see that as well, because what's the slope to the left of the graph of that point?
3.
Positive 3. What's the slope to the right?
-1.
And it's a sudden change, right? Suddenly we're changing from a positive 3 to a -1 slope. And so, in fact, yes, the function will not be differentiable there. So we'll say from -infinity to 2, union 2 to infinity. Okay, bless you. Questions about why that is again? Is that pretty straightforward? We're all okay with that? Okay, it's kind of pointy there. It's a sudden change in slope. That's the more important thing. The slope is suddenly changing from a positive 3 slope to a -1 slope. There's no transition. So the derivative would have a jump in it. Now, how do we take the derivative of a piecewise function?
You do it relative to the equation.
You take the derivative of the individual pieces. So what's the derivative of 3x minus 2? 3. What's the derivative of -x plus 6? -1. The arguments stay the same. Okay?
So the graph is just like absolute value.
It's similar to it, right? Because absolute value, you're going to have it's just going to be opposite numbers. But for this one, because it's going to be the same idea, though, yes. So if we were to graph that, 1, 2, for x values less than 2, the value of the function is going to be 3. So at 2, the value will be 3. So like this. And then for x values greater than or equal to 2, the slope will be -1. And technically here I shouldn't have an equals to, I guess, because it's at an end point, so it really should be like an open circle there. And so it's a jump, right, at 2. So we have a discontinuity. The derivative is not differentiable there. Actually, wait, is it 2? I think we can say it's equal to 2 there. I'm not sure about that. I'll have to check. But either way, we can see that the derivative is not continuous to 2. We have a jump. And so therefore the original function, we'll say, is not differentiable. Okay? The continuity of the derivative discusses the differentiability of the original function. The original function, you cannot take the derivative at 2 because the left and right here don't agree. The left-hand right side of the derivative at 2 don't agree. Okay? So that's the idea. That's how you can kind of see it graphically as well, besides just saying it's pointy. Okay, so in summary, or actually there's a theorem here, and then we'll summarize. Okay, if f is continuous, at x equals c, okay, wow, I have this written down incorrectly in the notes here. Sorry, it's not that. If f is differentiable, my mistake. Okay, if f is differentiable at x equals c, then f is continuous at x equals c. Okay, if f is differentiable at x equals c, then f is continuous at x equals c. Now, we have to be very careful here. If I make a statement like that, if f is differentiable at x equals c, then f is continuous at x equals c, is the reverse automatically true? No. No, right? So for example, you can make the statement like, if something is a square, right, then it's also a rectangle. Because squares have 4 equal sides, 4 equal angles. Rectangles only have just the 4 equal angles, right? So if something is a square, then something is a rectangle. But if something's a rectangle, right, it's not necessarily a square, right? We know rectangles that aren't squares. Okay? So that's the idea here. You can't automatically just flip the order and say it's the same thing. And that's very important to recognize. So if f is differentiable at x equals c, then we know f is continuous at x equals c. Okay? So thus, differentiability implies continuity. Continuity of a function, or you can just say continuity, does not imply differentiability. Just because something's continuous does not therefore guarantee it will be differentiable. What's a classic example that we saw?
Absolute value of x.
Absolute value of x, or the piecewise as well, okay? I'm going to give the absolute value, so I'm going to say e.g. f of x equals the absolute value of x. Absolute value of x is continuous everywhere, but it is not differentiable everywhere, okay? So just because something is continuous does not necessarily mean it's differentiable. Keep that in mind, okay? And that's it.
Cool.
So, I would like you guys to get started on that homework assignment that I gave you yesterday, either one of the two, okay? And then I will come around and help as necessary. Yes. Sorry? I'll let you know. Let me get this